Okay, so let's start the afternoon session. So the first speaker is Pawel Caputa from Warsaw University, and he's telling us about quantum complexity in the Krylov basis.
Thank you very much. So let me also start by thanking the organizers for giving me this great opportunity to be in Kyoto again, and also to presenting my work at this wonderful interdisciplinary workshop. So indeed, I will talk about quantum complexity in the Krylov basis, and I'll first give a short introduction and motivation, and then I'll introduce this notion of Krylov basis and the definition of complexity for states and operators, and I'll give some universal general examples, and finally I'll conclude and put some open questions. And this talk will be mostly based on two works. One with the group at the University of Pennsylvania with Vijay Balasubramanian, Javier Magan, and Qingye Wu, and that appeared earlier this year. And also a previous work with Javier Magan and my student in the University of Warsaw, Dimitris Patramanis, from late last year. So as we have already heard in several talks, this entanglement revolution in ADS-CFT that you can safely date it back to the works of Ryu and Takayanagi taught us a lot about holography and black holes from the quantum information perspective. And that's one of the main reasons we are all here. And the big question that people were posing, and we're still posing in this context, is how CFT states encode holographic geometry. And for that, it turned out to be very useful to use quantum information tools in ADS-CFT, namely notions of like Renyi entropies, entanglement, of course, entanglement of purification, pseudo-entropy, capacity, and so on. And one common feature of all these quantities is that they have a nice, useful, and good definition in terms of some well-defined object, like maybe traces or of powers of density matrix. But in my talk, I'll be telling you that sometimes we need more fine-grained probes that are especially sensitive to very late times in ADS-CFT, and they usually come under this kind of buzzword of complexity. So in my talk, I'll be asking the question whether there's also a good universal definition of complexity for quantum field theories, and in particular, something that we could universally apply to ADS-CFT as all these nice notions there. Okay, but before going there, let me remind you, why do we actually need, or why do we want this complexity in ADS-CFT? And there were, historically, there were two classes of setups that this complexity popped up. And one of them was this famous work by Hartmann and Maldacena, where they considered thermofield double state of this type that appeared many times already. And the time evolution done by either one of the Hamiltonians or left and right, such that it's non-trivial. And it was observed that entanglement entropy after some relatively early time of a single interval, entanglement entropy between intervals, say A on one side and B on the other one, saturates at some time of order size of the interval over 2. But actually the dual geometry to this state still has a non-trivial dynamics. There seems to be these slices inside the black hole that grow with time, even though the entropy already saturated. So this gave rise to this slogan by Lenny that entanglement entropy might not be enough to capture all the information about the dual geometry of the state. And then people started posing this question: what is the CFT dual of this growth of the Einstein-Rosen bridge? And the natural notion that Lenny came up with was something related to complexity of this thermofield double-state at late times. And the second setup where the notion of complexity came about is actually the notion of the operator growth. And again, similar setup where people studied this eternal black hole, for example, people were looking at this kind of sensitive structure, entanglement structure of the state, and comparing this to the states that are like slightly perturbed by some local operators on one of the sides, and these operators usually destroy the entanglement structure of the state. And this was called, this comes under the name of butterfly effect, such that the small excitation maybe at some very early times can cause a very big change in some other parts of the universe. And in this setup, people started talking about so-called precursor operators, and basically how to quantify the universally the size of the operator, or in other words, this operator complexity. So let's say we have some operator W that we do the usual Heisenberg evolution. And then basically the question was like, is there some universal notion of the operator size or the operator complexity that we could apply and study it in the context, in the useful context of ADS-CFT? And partial answers to this were given, of course. This discussion led to the development of the OTOC correlators that in some sense also measure the size of the operator as it grows in time. And you have already heard some, and they appeared in some of the talks before. But in general, basically this discussion on complexity led to several different notions that we can divide into these two groups. So one could be this complexity of states, where we usually mean about some complexity of formation of states or complexity of evolution of states. And there were many ideas, kind of a big group used ideas that can be dated back to the works of Nielsen, like geometric approaches to complexity. There has been also like this developments in Kyoto about path integral complexity and optimization, and also generally some notions of very good distance measures between states that we could use as the late time probes for the states. And on the other hand, for the notion of the operators, or this growth of the operators, operator size, or the measures of chaos, people use this relation between operator size, and people studied this notion between operator size and complexity. In the context of SYK, one could actually define a precise notion of what this size operator might mean. There were also some nice works on momentum of particles in ADS that could be related to the dual operator and the OTOC that I mentioned. But the hope is that once we develop some good measure of either of this complexity of the states or the operators, that will give us a useful number that we can compare with holography, let's say, then we will learn something interesting about dual geometry. So in particular, this complexity of states should be somehow related to the growth of the Einstein-Rosen bridge or the late time physics of black hole, maybe black hole singularity. Whereas this operator size, it seems like if we understand the good notion of this operator size, the expectations from the community is that it should be related to some physics of near horizon of black holes, and maybe basically this type of growth of the operators or scrambling near the black hole horizons. But still, this field is in some sense in a very active development. We still don't really understand the notions, many relations between these different notions, and also the notions between the gravity side. And this is kind of what my talk, or what part of my work will be based in the context of. Okay. So in this talk, I will discuss a notion or a class of notions of complexity that will be based on the so-called Krylov basis. And I'll tell you that this can be universally defined and computed in systems from quantum mechanics to quantum field theories. And I will present example results for both, for the states and for the operators, in precisely the setups I was talking about in a few minutes ago. And I will not give this will be mostly based on this work with that I mentioned at the beginning, but there has been also a very nice set of papers that are relatively recent. They date back to 2019 that studied this growth of operators in the Krylov basis, and this is pretty much these are pretty much the main papers that I'll refer to at the later stage. Okay, so let me start with this notion of the Krylov basis. So is there any questions? By the way, if there is any questions at any point, please stop me and I'll be happy to answer. Okay, so let me define this main object, namely the Krylov basis. And we'll be generally interested in the unitary circuit. So let's say we consider some state psi of t that we create by starting from some reference state psi 0 and doing the unitary evolution e to the minus iht. And such a state we can formally expand in all the powers of Hamiltonian acting on psi 0, and I will denote these states by this psi n, namely this span of psi 0, and then h and h squared, h third, and all the possible powers of h. And given this subset of states, what we want to do in this Krylov basis is we want to find an orthogonal or orthonormal basis, the so-called Krylov basis, recursively using the Lanczos algorithm. So basically, what that means is that once I consider this initial state psi 0 and all the powers of h, I can pretty much do the usual Gram-Schmidt orthogonalization to create the Krylov basis Kn. And more precisely, this Lanczos algorithm goes as follows. So I first define some state a n plus 1 recursively by action of the Hamiltonian on some state Kn, and also I subtract another state Kn minus 1 with appropriate coefficients ans and bns. And then I normalize the state an by this coefficient bn minus 1 to this Krylov basis vector Kn. And actually, these two states, these two coefficients, ans and bns, they are so-called Lanczos coefficients, and they are basically an, these coefficients an are just expectation value of the Hamiltonian in the state Kn, and bn is just a normalization of this vector an. And I do this algorithm recursively starting from n equals to 0 all the way up. So such that b0 equals to 0, and then k0 is this initial state that I started with. Okay, so this is the algorithm that then you can implement, and step by step, you can find this orthonormal basis. And as a product, you not only find all these Krylov basis vectors, but you also find these Lanczos coefficients, an and bn, that will be very important in the rest of my talk. And basically, I told you about some Hamiltonian evolution, but actually the setup is very general. So we can just start from any state psi 0, and then this is some unitary e to the iht, but it doesn't need to be your Hamiltonian. It can be just some circuit Hamiltonian, and t does not need to be also your real time. It can be just some circuit. Okay. And basically, by this Lanczos algorithm, by construction, the Hamiltonian or the circuit Hamiltonian in this basis becomes tridiagonal. So the algorithm was such that when an acts on this kn, there's some diagonal part an, and then off diagonal pieces with this coefficients bn plus 1 and bn. So in other words, if you compute the matrix element of the Hamiltonian in this Krylov basis, it has this tridiagonal form that on the diagonal we have ans, and here we have this bns. And this is usually called Hessenberg form. So basically, once you have gone through this algorithm, once you constructed all the bases, then you can expand your state that you are interested in this Krylov basis in this appropriate way. So this is the basis Kn, and then I denote this Kelly phi n, the coefficients of the state in the Krylov basis. And by construction, they are actually probabilities. So in other words, the absolute value of this phi n squared sums up to 1. Okay, and also by construction, by this algorithm, this tridiagonality of the Hamiltonian, we can actually derive the Schrödinger equation or discrete Schrödinger equation for this coefficients phi n, namely by taking the derivative of the state with respect to t and using the action of the Hamiltonian in the Krylov basis, we derive that the coefficients of the state, they satisfy this recursive equation for each n with the Lanczos coefficients that we get also from the algorithm. And the boundary condition is such that this coefficient n at the time t equal to 0 projects on the 0 vector. So in other words, like at t equal to 0, we have to be in our state psi 0. Okay, so this is basically the algorithm. And this is the construction, how to expand your state in the Krylov basis and how to find these coefficients. Let me also mention one important thing is that actually these Lanczos coefficients that I told you that you have to go through this recursive procedure, they are completely encoded in the so-called return amplitude, or depends on the community, you sometimes call it autocorrelator or log-Schmidt amplitude, namely the projection of the state psi of t on the initial state psi of 0. So in other words, the expectation value of e to the iht in this initial state psi 0. By construction, also in this state, this becomes this return amplitude is this 0 n equal to 0 coefficient. So it's n equal to 0 of t. I use some convention that I'm actually taking the star of as 0 because I'm just projecting the other way. And basically, the moments of this return amplitude or the log-Schmidt amplitude, they can be computed from this autocorrelator. And basically they have this form. So there are also expectation values of the Hamiltonian to the power n in your initial state psi0 or k0, this algorithm. And then basically once you know the moments, or once you know the return amplitude, you can easily do there is an algorithm also to read off the Lanczos coefficients ANs and BNs from the moments. And this goes also through something called the counting of Dike paths that appeared in the previous lecture. And basically, just to show you an example, here this nodes at the bottom denote this curve, these moments mu. So this is mu0, mu1, mu2, mu3. And then basically in order to compute the relations between these mu's and parameters A, we need to count how many independent ways we can, in how many independent ways we can get to the moment mu n. And basically, if we go all diagonally, we take some IB coefficients. If we go horizontally, we go I as 0. And then basically for each path, we just multiply all the values on the nodes of this path to get the explicit relation. This is just some well-defined computer science algorithm of how to get ANs and BNs from these mu-ns. So basically, all the important information that we will want in our setup is also encoded in this return amplitude, and this will play an important role in the rest of my talk. Okay, so let me, before I move on, and basically, if I know these coefficients ANs and BNs, then I can solve this Schrödinger equation with this boundary condition, and this will be my main objects. For defining complexity, I'll be working with these coefficients ANs. I'll be working with these coefficients phi n's in the Krylov basis, and then they can be extracted from this return amplitude. I just want you to remember that. Okay, and then I told you that you can do this definition of complexity both for states and operators. I haven't told you what's the definition of complexity yet, but before going there, I'm just going to quickly describe how you basically do the same for the operators, and then I'll define the complexity for both, for states and the operators. But let me just tell you how we define this Krylov basis for the operators. So namely for the operators, we are interested in this Heisenberg evolution, which is given by this. And basically the formal solution again is given by some operator at time t equal to 0, sandwiched by this e to the iht, e to the minus iht. And then formally again, we can expand the operator in this different powers of basically in these nested commutators of the Hamiltonian with the original operator at 0. And then in this language, it's useful to define the super operator, namely this Liouvillean that acts in the space of operators by taking the commutator of the operator with h. And basically this operator at time t can be formally written as e to the I Liouvillean times t on the operator at t equal to 0. So in other words, all these nested operators are just different powers of the Liouvillean acting on the original operator. And then given again this Krylov, given this Krylov subspace of the operator and then different powers of the Liouvillean, in this case, acting on O, we want to define the basis. We want to create the Krylov basis that corresponds to each of these operators. And in order to do that for the operators, we must pick an inner product in the space of operators, and one standard form, there's a freedom related to that, but one standard form that appeared in the literature is called Weitman inner product, where we basically compute the correlator of the operators. We compute the thermal correlator, but we move one of the operators by beta over 2 to on the thermal circle. So this is basically the inner product that I'll be choosing in the space of these operators. But once we have done this, basically the algorithm goes pretty much the same as before, except that it can be taught as a subset of the previous algorithm, in the sense that if for most of the inner products, we actually choose the trace, like here, which is the thermal trace. And basically that means that when we compute the expectation value of the commutator of the Hamiltonian and the operator, we can eliminate the diagonal piece. So in many choices of the inner product, these ANs don't appear, and only we can focus on these BNs. And then in that case, the algorithm goes as before. So we define this step by step for different ends, then we normalize and we end up with these Lanczos coefficients. Then the state that corresponds to the operator at time t can be taught as e to the I Liouvillean of t acting on this initial state. We expand that again in this Krylov basis for the operators. And then basically from the algorithm again, we get the Schrödinger equation as before, but without ANs. We need to solve it with particular boundary condition. And then all the knowledge about this Bn is actually encoded in this autocorrelator of O of t and O of 0, which is again this 0 coefficient of the expansion of the state in the Krylov basis. Notice here, I'm using a slight convention that, that you can find in the literature. And then basically this curly always means that I'm using a specific inner product. Okay, so basically this is a summary of this Krylov basis. On one hand, I'm interested in this complexity of states. On one hand, I'm interested in this expansion of the states in the Krylov basis. On the other hand, I can do this expansion of the operators in the Krylov basis, and the main role will be played by these coefficients that squares are just probabilities, so they sum up to 1. The same here, they sum up to 1. I'm using a slide. This is really just a convention. So if you'll be studying this, looking into our papers, if you're interested, and papers in the literature on the operator growth, you can, sometimes it's annoying to keep track of this I to the n, but this is just the two different conventions that appear in the papers. And basically we need to solve this Schrödinger equation with the Lanczos coefficients, that of course depends on the initial state K0 or O0 in this case, and also your Hamiltonian H or your Liouvillean L. And then the knowledge is encoded in this return amplitude or the return amplitude for the operators. And obviously there are connections. So for example, we can study states where we take some Heisenberg operator and act on some initial state. Or for example, this Weidmann inner product that I talked about for the operators, you can actually, in order to reproduce that answer as the complexity of states, you can just consider this thermofield double with operator inserted on the left, but also moved a little bit on the thermal circle. And then basically the return amplitude that comes from this state will be the same one as for the operator, choosing the operator in the with the Weidmann inner product. Okay. Good. So let me finally, after this basic introduction to Krylov basis, maybe for some of you it was something really familiar that you're familiar with, let me finally define for you this so-called spread or Krylov complexity. So actually the original definition comes from this paper by Parker and collaborators. And basically they, because of the Schrödinger equation, this physics of the growth of the operator, it can be mapped, or it's actually physically mapped into a motion of a particle on a certain chain. So let's say if we just take a chain with nodes that are labeled by these amplitudes of the expansion of the operator state in the Krylov basis, then we can, links on this node from the Schrödinger equation, they can be thought about as basically transition amplitudes between different nodes. And because we have this probabilistic interpretation, we can think about it in the following way, that this particle that is hopping on this chain is basically telling us like how which orthogonal and complicated state in the Hilbert space we need to represent our operator at time t. So for example, the farther the initial state is psi0, that means that you are in your initial operator or initial state in the Krylov basis, but then once time progresses, the particle moves to the right. And then basically the farther it is to the right, the more state you need from the Hilbert space to represent the operator. Okay, so basically they introduced this natural working definition of complexity as the average position of this particle on the chain. And they call this Krylov complexity. And I will also be using that definition. So in other words, I'll be computing the expectation value of n, this number that labels each of the nodes, in this probability distribution of the coefficients of the state in the Krylov basis. And this will be universal definition both for states, this C psi of t. So I'll be solving this Schrödinger equation with ANs and BNs, or we can also solve the Schrödinger equation for the operator only with BNs. And then once we find these probabilities, we just compute the expectation value of n. And that's really the definition of the Krylov complexity or the spread complexity. Let me just comment that sometimes it is also useful to think about this complexity as an operator. So once we constructed this Krylov basis, basically we can think about this operator like this, and then the complexity is just expectation value of that operator. Okay, maybe two more comments before I go to examples. So what kind of complexity you can, I was just giving you some motivation that basically this is a natural distance measure in this Hilbert space that the position of the particle on hopping on a chain is a natural measure of the distance between this initial state and more complicated state in the Hilbert space. But there's another way of making this intuition precise. Namely, we can define the complexity as a spread of the state, this initial state, in the Hilbert space. So how would you go about in this definition? Basically, what we showed is that you can choose an arbitrary basis Bn such that you index it in some in some way such that B0 is your initial state, and then you have B1, B2, B3. This is your basis in the Hilbert space, and then you can define a family of cost functions by basically taking your state that you evolve and projecting the state on this basis. Okay, so this naturally the projection of the state on the basis, these are just some probabilities. And then this coefficient Cn that you can choose here, the important thing is that they should be non-decreasing. So they can be, in particular in this choice of Krylov complexity, we choose the Cn's to be n, but they can be n squared and so on. And basically, if you choose your complexity in this way, if you minimize over all choices of the basis, then this is a nice notion of the complexity or the spread complexity that tells you how your initial state spreads under the unitary evolution in the Hilbert space. And basically for discrete time evolution, we can really prove that this Krylov basis gives you the minimum of this cost function. And also for continuous time, we can also give some, for finite but not very long times, we can also give a proof that Krylov basis indeed minimizes these cost functions with positive Cns. Okay, so that's one comment. And another comment is that once we expand the state of or the operator in the Krylov basis, then actually the important thing is that we get this probability distribution that characterizes the full evolution of the state. Okay, so these phi n's, their squares, they have all the information of how the state is spreading or how the state evolves in your space. And basically, there's no, like in with every probability distribution, there are many useful tools. There are many useful quantities to extract interesting information about the probability distribution. So this K complexity or this Krylov complexity is one quantity, basically the average position in this probability distribution. But there are other quantities that are also very useful to probe the state and the operators, namely the so-called K entropy, where we basically take this probability Pn and we just compute the information content of the distribution, or in other words, just Shannon entropy. We can also compute the variance or K capacity, or actually we can take the exponent of this K entropy and so on. And there has been many interesting tools in the literature that basically were used to characterize this growth of states and the operators in the Krylov space. So that's just a comment. Okay, yeah, let me go to examples, and if there's questions, it's a good time to.
Sorry, this is very stupid question, but so you take minimize in Krylov basis. And in my understanding, when we fix a Hamiltonian, then a Krylov basis is also determined.
Yes.
So how to minimize it?
Oh, I'm sorry, maybe it was not clear. I'm minimizing this cost function over all choices of the basis. Yes. So okay,
I understand.
So not all the bases will be Krylov bases. There will be like some bases that can be, that will be Krylov plus something orthogonal and so on. But if we choose this, as long as the Cn's are positive, we can show that the minimum is always attained by the Krylov base.
I understand. Thank you.
Thank you for this clarification.
Sir, I had a question.
Yes. Oh.
I'm audible. If we have a perturbative Hamiltonian, I mean, with some perturbations added to the Hamiltonian, then how do we define the basis?
Sorry.
If we have a
this is an online question. Okay. The question was if we take the perturbative Hamiltonian.
Yes. How do we define how do we define the basis and the neighborhood?
If I understood the question correctly, what happens if I take some Hamiltonian that is maybe just some particular Hamiltonian plus a perturbation?
Yes, sir.
Yeah, okay, then of course, then the algorithm works exactly the same way. You just basically expand this, you take this Krylov subspace of all the powers of the Hamiltonian, and then I guess if you take your perturbation to be small, you truncate it at some particular first order. I guess that's what you would like to do.
If it's time dependent, that is.
Sorry,
If the perturbation is time dependent.
if the perturbation is time dependent. Yes, this can also be done. It's actually quite interesting. So yeah, basically in that case, you first have to do something called like Magnus expansion. And then once you have done this, then you can write your state again as exponent of e to the minus h times time. And this h will be different than, it will be some integral of your perturbation in time, and then you do this Lanczos algorithm and Krylov subspace with this Magnus Hamiltonian in the exponent.
Thank you, sir.
Next question.
Mm-hmm.
So actually, yeah, I also want to ask about this one. So first part, so C, this one. So yeah, actually, yeah, I understand we can, if we change the basis arbitrary and Krylov basis, minimize something, but I still don't get the meaning of that. So actually, what's it? So I think I expect your claim is Krylov is a very special basis and it's minimized something, but it is a minimized complexity or minimize. So
sorry.
I want to know the meaning of that.
So okay. So basically, in this comment, I wanted to define the complexity as the spread of a state. And so basically, let's say I have some initial state, some state somewhere in the Hilbert space, and once I do the evolution, this state starts to spread. Okay, so it kind of has non-trivial overlaps with other orthogonal vectors and so on. And what I want to do is like I want to in some way I want to quantify the complexity of the spread of the state in the Hilbert space. So I was trying to argue like one way to quantify this is basically choose some basis in your Hilbert space, Bn, whatever that basis is, such that this initial vector in this B0 in this basis is the same as this initial vector psi0. Okay. And then basically take the state psi of t and then project it on this basis that you have chosen. Okay. And then basically you can compute the cost associated to basically this state with respect to this basis Bn by this, basically taking these probabilities, some of them, and then putting some non-trivial coefficients Cn that are like non-decreasing. Okay, so basically they will be counting for you, like what's the support of the state psi c on B0, what's the support on B1, B2, and so on. And as long as these coefficients are positive, then this cost function will be increasing as long as you are using higher Bn's in the cost function. Okay. And then, but of course, we don't want to, in some sense, we don't want to have the dependence of the complexity on the basis so much. So basically, we want to minimize this, to take the value of the complexity for this spread of the state in the Hilbert space. Now you want to minimize this cost function over all choices of this basis B.
Okay, yeah. The important point is the Cn is set to the n, and for that, we get such kind of.
As long it can be n square and whatever.
Such an increasing function.
We can, as long as it's non-decreasing, we can show that it's minimized for the by the Krylov basis.
Okay, yeah. Thank you.
Yeah, great. Thanks a lot for clarifying questions. Okay, great. Let me then go to the examples. Okay, so as I was arguing, these interesting states for which we would like to use this notion of complexity, they started from this question of time evolving of the thermophile double state. So again, I start from some thermophile double, where z of beta is just a thermal partition function. This is, of course, the purification of the thermal state. And I want to consider some state that has a non-trivial evolution of the thermophile double. We can either, for this evolution, we can either use the sum of the left plus right Hamiltonian, or we can choose only one of the Hamiltonians. That's fine. Okay, and let's basically now compute the spread complexity for this object. And so in other words, I told you by this algorithm, we first need to expand this state in the Krylov basis. And once we've done that, we extract the coefficients, and then we compute either K entropy, K complexity, and so on. And as I told you, all the information that was relevant somehow for solving the Schrödinger equation or for determining the coefficients is encoded in this return amplitude. So return amplitude is the overlap between the state psi of t and the state at psi of t equal to 0, which in this case happens to be the ratio of the partition functions, the thermal partition function, analytically continued to the time, the real time, so beta minus it over z of beta. And this is the amplitude that usually appears in the spectral form factor that maybe some of you know very well. So basically now the spread complexity for this time evolution of the thermophile double state is based on this return amplitude that is just a spectral form factor. And this is of course non-universal. But once we know the thermal partition function, or even in some limits, then we can study what is the growth or the spread complexity for this thermophile double in these limits and so on. And but I'm going to show you the result for evolution of the thermophile double state in for some random matrix theory. So in other words, we can, for example, take the Hamiltonian that is like some n by n matrix, random, chosen at random. So this is not important, it's some random numbers. And then it should be Hermitian, and we can choose it from the Gaussian or for one of the ensembles. So Gaussian, symplectic, orthogonal. And then of course we can easily diagonalize this numerically. We can compute the spectral form factor, we can compute the moments and extract the Lanczos coefficients and so on. But actually there's also a nice shortcut in order to extract this spread complexity in the context of finite dimensional spaces. Namely, as I showed you in this Krylov, once I go through this procedure, in the Krylov basis, this Hamiltonian that I'm using should get this form. This is the so-called Heisenberg form with these ANs and BNs. So if we manage to put the Hamiltonian into this form, we can rid of ANs and BNs and then exponentiate it and apply it to our initial state and automatically rid of the coefficients that will be sufficient to compute complexity. And actually, so in this numerical example, there exists very efficient. So if we want to do it for some very large matrices, let's say 1000 by 1000, then there are some very efficient algorithms and libraries in Python and Mathematica to put a matrix into this Heisenberg form. So basically, this is what we were doing in this paper. And another thing is that in these libraries, basically your initial state is usually put into this form 1, 0, 0, 0 as this vector. So when you put the Hamiltonian into this form and exponentiate it, and you apply it into this vector, you need to make sure that first you mapped your thermophile double state into this 1, 0, 0, 1 vector. So that's the intermediate step. But once you have done this, you apply it and you rid of immediately all the ANs and BNs and the coefficients phi n's for the complexity. So this can be done numerically in this example. Okay, and let me show you how what kind of answers do we get for this example. For this time evolution of the thermophile double for these random matrices, we studied the GUE Hamiltonian in the GUE up to size of the matrix 4096 for some stability and numerical reasons. And then here we plot the Lanczos coefficients ANs as a function of n over the capital N of the size of the matrix. And for comparisons, here we have Lanczos coefficients Bn as a function of n over capital size of the matrix. And maybe it's better to see a bit more detailed evolution at the early times. So you can see that actually both of them grow initially linearly, but then ANs very quickly saturate. They basically go to 0, but BNs saturate to some constant. And then finally, A's just numerically stay at 0, but BNs go to 0 as this function of n over n. And maybe I want you to remember for the analysis of the, or maybe for a more analytical analysis, you can check that there's this special combination between ANs and 2 times BNs that, initially it's some non-trivial number, but then finally it goes to some constant. And this combination an being equal to 2 times bn, it can be understood nicely in analytic examples, so that I will go into in a moment. So please remember that. So basically, this is just some generic behavior of ans and bns in this evolution of thermofield double for random matrices. But you can check that actually once you now exponentiate the matrix and find the evolution and find the coefficients, you can study how this complexity for this state evolves in time. And there's some universal early time behavior of this complexity. Basically, it grows quadratically in time for some initial period of time. But basically, for the full range of time that we studied, so this is now this Krylov complexity or spread complexity for this thermofield double state divided by n, and as a function of t over n. Here on this plot, we presented many examples, like average over this many examples of n from 1024 to 4096. And you can see that actually, sorry, I hope it's visible. It's plotted here for different temperatures. So this is for beta equals to 0, this is dark blue, and for beta equals to 10 is this lower one. And basically it has this universal 4 regimes of the evolution that, once you know this plot, you can go back to ans and bns and you can determine what is the mutual behavior of these ans and bns that correspond to these guys. And then the 4 regimes are basically the ramp. So there's this initial growth. Then there's the peak. After the peak, we have the slope, and then there's a plateau. And basically, I want you to compare this to the so-called spectral form factor. So for the same setup of these random matrices, we can plot this log of the spectral form factor as a function of log t. And there also we have these 4 regimes of slope. Then there's a dip, there's a ramp, and the plateau. And basically, we have, so basically they are the same, this is the same setup, the same evolution, and then just these 2 quantities, spectral form factor and complexity for comparison. And here you might notice that actually there's some interesting physics that has to do with this, ramp and the dip in our example. So for example, you see this for beta equals to 0, we have this behavior with the ramp, peak, and the plateau. And then on the spectral form factor, we also have the slope, dip, and the ramp. But there's this curve here and curve here that does not show the peak and the slope. And basically what we have done here is we check that if we draw, this is due to the correlations within the random matrices. So for example, if we just draw the eigenvalues of these random matrices, but at random from just Dyson distribution, then we basically get rid of this peak and the slope, and also we get rid of the dip and the ramp in the spectral form factor. So basically this physics of peak and slope is the physics sensitive precisely to this, this behavior. And actually also, as I was telling you, there was this picture for the growth of the operator that, 7 minutes long. There was this picture for the operator that basically initially the operator was supported at this initial state, psi equals to 0. And then as time evolves, the operator grows in this Krylov basis. So for the random matrices, we see that this initial operator at the initial state basically spreads ballistically to the more complicated vector in the Krylov basis. And basically the time where the operator reaches this most complicated state in the Krylov basis, that's precisely this peak. Then operator basically starts going back, this evolution, the support of the operator in the Krylov basis starts going back. And this is precisely the slope here in this picture. And then finally, the support of the operator, this probability distribution becomes like just uniformly distributed. And that's exactly the plateau in these pictures of the complexity. Okay, so let me just also show you an example for the growth of the operator. And this was actually the first done in the paper by Parker. Namely, they considered some operators, a gamma in the SYK, in the large Q limit, where this return amplitude in that case can be simply, has this universal form as 1 over cosine hyperbolic to some power eta times pi t over beta. And then basically, once you go through this Lanczos algorithm and through this Krylov basis for this return amplitude, you can find that, as I told you, for the operators, we can get rid of, so this is for the choice of the White-Manine product. We don't need AN coefficients, but we can find coefficients BN. And we can also find these amplitudes, probability amplitudes in the Krylov basis. They have this form. And they notice that actually, they notice two things. One is that the Krylov complexity has this particular simple form. It goes like sine hyperbolic square times alpha t, where this alpha is given by 2 pi over beta. Pi over beta, 2 times alpha is 2 pi over beta. And then the for late time complexity of this operator, or the size of the operator, grows exponentially. And that led them to, for the operators, that led them to this universal operator growth hypothesis. Namely, they conjecture that actually the maximal possible growth of these Lanczos coefficients in any systems is linear. So basically, these BNs can at most go as something alpha times n plus something order 1. And basically, they claim that this is saturated. So when the growth is linear, this is saturated in the maximally chaotic systems in a sense of out of time order correlators. And when this is saturated, basically they claim that this Krylov complexity grows exponentially, and then this lambda, the Lyapunov exponent from this K complexity, is precisely equal to the lambda that you get from the OTOC. So this is 2 pi over beta. And they studied that numerically in some free theories, integrable models, and SYK, and that led them to this universal operator growth hypothesis. So that's another example where you can study this Krylov complexity. How much time do I have? 5 minutes? Okay, so let me just quickly go to a simple analytic example where you can actually find the solution of this Lanczos procedure based on symmetry. And basically, we can consider a general, let's say, consider an SL2R algebra, and then take the natural basis in this algebra given by just some highest weight state H, and then all the powers of L minus 1 to the power n. We can check that in this basis, this L0, L1, and L minus 1, they have this particular action. So actually, once we take the Hamiltonian, general Hamiltonian in this for this Krylov basis evolution to be of this form, say gamma times L0 plus alpha times L1 plus L minus 1, and then the Krylov basis as Kn times H times n, where this Hn are basically this natural basis in the algebra. Then actually, this Hamiltonian in this particular basis is immediately tridiagonal. And then we can abstractly rid of the solution of the Lanczos procedure and the Krylov basis coefficients and so on without going to any physical applications of this SL2R algebra. I'll go, actually, it will be important that there are some non-trivial applications, but this slide, I just want you to consider this abstractly. And if you take such an operator, then you can immediately see that ANs from the definitions, they are the diagonal pieces. So diagonal pieces are basically these coefficients. They go like times gamma times this n plus h. And BNs have this square root form with some coefficient alpha that comes from this Hamiltonian. And basically, for such an operator, you can just use the standard Becker-Campbell-Hausdorff to apply it to this highest weight state and to rid of immediately these phi n's, and check that they indeed solve the Schrödinger equation with the correct ANs and BNs. And then for this subset, you can compute this Krylov complexity. So the expectation value of n with this probability distribution, it has this general form. So it depends on this gamma and alpha of this Hamiltonian in the following way. So it actually is the sine hyperbolic alpha times t times the square root. And now you can see the important role of these ANs. So ANs are basically non-trivial when gamma is non-trivial. These are the coefficients of ANs. And then we have this exponential growth for late times if gammas are smaller than 2 times alpha. We have a quadratic growth where these ANs are nearly like 2 times alpha times n, or in other words, like they are 2 times Bn. This is actually the example where we saw in the random matrix model I wanted you to remember. And in this case, the complexity grows quadratically and not exponentially. And in principle, we can actually go to periodic regime where the sine hyperbolic becomes sine when this gamma is larger than 2 times alpha. Okay, So is this useful, this symmetry example? Actually, yes. So you can check that for gamma equals to 0, that means ANs are 0. You can check that this growth of the operator in the SYK model that was based on this return amplitude that was sine hyperbolic is precisely this SL2R coherent state or SU1,1 coherent state. And so in other words, basically the state that corresponds to growth of the operator can be written as basically this coherent state expanded in the natural Lie algebra basis, given that the basically this coordinates in the basis rho and phi are given by simply this 2 times alpha t and phi equals to pi over 2. So in other words, the solution of Parker can be read off immediately from this coherent state if we see that this growth of the operator is just some geodesic in this Hilbert in this phase space of coherent state, phase space spanned by the coherent states. Okay, so I think basically what I wanted to just quickly say is that there's a natural way of associating a geometry now. Maybe this is for people that studied complexity before and this relation to the geometry. By namely taking these coherent states and considering the so-called Fubini study geometry associated with coherent states. And in this geometry, the growth of the operator corresponds to a geodesic, as I was arguing. So in these coordinates that for SL2R becomes just hyperbolic disk, the operator growth is just this linear trajectory along some direction. And what we observed is actually this Krylov complexity is proportional to the volume that is encaptured by this radial direction 2 times alpha t. So in other words, we found this universal relation between the Krylov complexity and the volume in this phase space, and we also found it for other states. So in my last maybe slide is this cartoon. So basically, this when we consider this information metric or this the phase space metric given by hyperbolic geometry, or this is this Fubini study, then the growth of the operator is basically some geodesic that starts at t equal to 0 at this origin and then goes like along this trajectory. And then when we compute this Krylov complexity is proportional to this volume that is encaptured by this position rho equals to alpha to t. So this is the relation between the Krylov space and then the Krylov complexity and this volumes in this information geometry. Okay. These are the examples. Let me leave the conclusions and open problems here on the slide, and thank you for your attention.
Yeah, thanks, Pawel, for very interesting, nice talk. So is there any question?
Can I ask some simple minor question?
Yes.
Oh, is it okay?
Is it online again?
Oh, yeah, yes. It's online, yeah. Let's see, about this minimization of minimizing the complexity to get the Krylov basis.
Yes.
That's some people asked in that expression. So the minimization of the basis B, right? What to do with the T? It shouldn't be for fixed T, right? Because
no.
Right? Because if you fix T, you can always choose B1 to be that state. So how the minimization works?
Yeah. So it has to be done for some finite amount of time. It's such that your state in some finite amount of time has to be supported in this basis. Of course, if you choose it for fixed T, then you're gonna get something.
Yeah.
This will not do the job. So.
Something like you minimize, and so minimization is something you have to be clever, right? You just have to take different T's and
it's
so on.
very easy to see how it's done for the discrete time. So like at discrete time, you just apply, one time passes, you apply one Hamiltonian to your state. Yeah. You find a new, you orthogonal, you do Gram-Schmidt, you find one state. Then you do another. You do another step, you do the same, and you check that all these guys that you can do this minimization for finite number of steps are just given by Krylov basis, and they will support your state for this finite amount of time.
Okay, and then continuum limit will just gives
exactly. In the continuum limit, it's a bit more tricky because you have to tell me like how do you compare the states, and we basically in the paper we took different powers of derivatives. This cost function at evaluated t equal to 0. But then, of course, you need to do it for finite amount of time to check that the basis that does the job is the Krylov basis. But it's very important. Like there were many confusions about this exactly at the beginning. So thanks a lot for this.
Okay, great. Thank you. Thanks for good talk.
Yeah, I have a comment about your example involving SL2R algebra.
Yes.
So the condition gamma equal to alpha is exactly the same as the condition under which the Hamiltonian becomes the Hamiltonian of the sine square deformation.
Yes,
So do you have any comment about it?
Well, yeah, I know it's SSD, and then also for general one, you can just do this like Mobius deformation of, if you consider this, for example, as some CFT, say 2D CFT example. I have thought a little bit about this, and I think this is related to basically the choice. So this is, if you want to think about it in the context of, say, operator growth into the CFT, this is related to the choice of the inner product. And then somehow, like when you go from, because, you know, for example, in CFT, like your origin Hamiltonian is, say, L0 or something like that. But then once you choose a different inner product, then you want to go into this tridiagonal basis, and in the tridiagonal basis, your Hamiltonian becomes this, you know, L0, L1 plus L minus 1, say for SSD or for Mobius with this non-trivial coefficient. And somehow this in the CF geometrically going from you know, the usual radial quantization basis to this Krylov basis seems to be like just a different quantization, like north-south type of quantization, like you have in SSD or in Mobius. That was my understanding.
Yeah, thank you. And I have another question. So I think SL2R has both continuous and discrete series, right? So, but
yeah, so this was for discrete series.
I see.
It's interesting to go to other representations and also like other coherent states. We sort of thought a little bit about it,
but in the continuous case, the states are non-normalizable, right?
Yes. Yeah, we haven't studied that yet carefully. And definitely, these discrete series representations of SL2R, of Heisenberg-Weil, of SU2, they play important role in this Krylov construction. But there's still a lot to understand in this coherent state. So I have nothing.
Yeah, thank you.
Thank you for nice talk. Could you go back to the slide where you compare the degree of complexity and spectral form factor?
Yes.
Thanks. Yeah, as you mentioned, there are some typical time like deep time and plateau time.
Yes.
And as far as I remember, it can be specified with respect to the matrix rank and the inverse temperature.
Yes.
And my question is, so is there some similar scaling for your complexity?
Yes. So maybe I was not very clear about this, but what is important is like it scales with the like exponent of the entropy, the time that we reach this.
I see.
But actually, it was a little bit difficult to compare numerically whether this time, like let's say for the deep of the spectral form factor, is exactly the same as the top part of the complexity.
I see. So maybe the origin slightly different.
Yes. There might be some factors between them, but definitely it's like an exponent of the entropy.
Yeah, it looks very interesting. Yeah. Thanks.
Any other questions?
I'm very curious about the you showed in the SL2 algebra, and you showed that in the such gamma larger than 2 alpha, it becomes to it shows a periodic oscillation or something. Yeah, actually, I didn't get the I didn't understand well about the mathematics and this theoretical thing, but I want to know what physically means that. So what kind of physical system related to that, or what interesting thing going on? Yeah.
So that's a good question. So actually in the paper, for the SL2R, because this is of course infinite dimensional, and then this is a formal continuation, so where this becomes imaginary. But actually in the paper, we checked explicitly an example where you can, in actually this regime where BNs and ANs, they have particular scaling of this analytically continued one, and this corresponds to SU2 coherent states. So in other words, if I take this this Hamilton to be built of say J free and J plus J minus, then this is the physical, for of course all the physics enters into this gamma and alpha in the algebra, and then once we study the operator based on this SU2 algebra, this is precisely this has the oscillatory behavior. So in particular, for spin J, there is only finite number of Krylov basis vectors. These BNs, they don't grow linearly with n, but they go to the maximal one, and so on. So
you mean that the complexity does not evolve in such case, right?
It evolves, but it's oscillating.
Oscillate and actually, yeah, okay. Or other side, it goes to the exponentially or more rapidly, yes. But it stay around some certain value, right?
Well, so it's just like it's zero, like by construction, it's zero initially, then it grows quadratically, then reaches some peak, exactly where you reach the most complicated state. And then for spin J of SU2, you have like 2J plus 1 states. So once you go to the most complicated one, then you start coming back, and then you go. And basically, it's the same picture like here, but then this hyperbolic space becomes a sphere. So then the evolution of the operator is just an evolution of the operator from the sphere that you just come back, to the most complicated one, and then you return again. So that's why it's oscillating.
I see. Thank you.
But for physical application, it's actually quite interesting. Like it turns out that this SU2 coherent states, we could use them, for some free fermionic examples where we studied like some reference ground state and target to be some vacuum of I don't know, some free fermion like models where we study, for example, SSH model or something like that. This was exactly the SU2 coherent states.
I see. Thank you.
Now the time is over, so let's thank speaker again.
Thank you.